All right, so using the reciprocal identities, we talked about those yesterday. The identity means that they're mathematical synonyms, right? You can replace one with the other. And there's three sets of reciprocal identities. Sine and cosecant are reciprocals. Cosine and secant are reciprocals, and then tangent and cotangent are reciprocals. So you want to know them in both versions, right? So sine is 1 over cosecant. Similarly, cosecant is 1 over sine, so on and so forth. But here's what else I want to mention before we go on to example 1 is once you have these memorized, you can actually use them. This is why they're called fundamental identities. They're the building blocks of other identities. Once you have those memorized, you can use them to derive or even prove, which is what we're leading towards, other identities. For instance, if you take this one, sine equals 1 over cosecant, you can actually now multiply both sides by cosecant if you want, just like you would do if you were solving a conditional equation. And what would happen? Well, on this side, they would divide out. You'd end up with 1. And over here, you'd have cosecant of theta times sine of theta. So apparently, what's cosecant of theta times sine of theta? 1. And that should make sense because, no, not inverses. Reciprocals of each other, right? The reciprocals of each other. And anything times its reciprocal is what? 1, right? 5 times 1/5, cosecant times sine. So that's a brand new identity. Do you want to memorize that one? Cosecant times sine is 1. Do you want to memorize that? No, I'm not going to stop you, but no, because you can derive it or obtain it so easily if you needed to from the fundamental identities. So you don't want to have to memorize every single identity we come across. Memorize the fundamentals, and then you can manipulate them. Because of the commutative property of multiplication, you could actually flip that around and now say sine times cosecant of theta is also 1. That's a brand new identity, but you don't want to have to memorize that one either, okay? So what I was saying yesterday when the bell was cut me off rudely is I'm going to show you actually how we're going to prove that this exists. And this is going to give you a taste of what proofs are. Now, mathematical proof and proof outside of a math classroom are not necessarily the same thing. Because like if I wanted to see, if I wanted to prove that it wasn't raining outside right now, I could look outside my window and say, it's not raining. That's proof that it's not raining outside. But that wouldn't necessarily be true, right? Because I'm only looking outside my window. Asia, look outside your window. Is it raining outside your window? No, it's not raining outside Asia's window. So because it's not raining outside these two windows, it must not be raining outside. Is that true? No. What about in Mrs. Lincoln's room? She has 2 windows. I'd have to go check her 2 windows. And then Mr. Kilford room, Miss Girl. I could check all the windows on campus and look outside all of them. And if it wasn't raining outside all the windows, then it must not be raining outside. Yes? No, because are there other windows in New Braunfels? I'd have to check all the windows in New Braunfels. And then if it wasn't raining outside all those windows, then it wouldn't be raining outside, right? No, because there's more windows in other parts of the world. Crap. Could you check all the windows in the whole wide world? Physically even? And even if you could, if it wasn't raining outside any of them, could you then say it wasn't raining outside? No, no. So whenever you check outside individual windows, that's called verifying, case by case verification. Okay, that's just seeing if it's true in that one particular case. There is no amount of verification that constitutes a proof in mathematics, right? So you can spend the rest of your life walking around checking window after window after window and making a list of windows outside of which it's not raining. And on your deathbed say, oh, therefore it's not raining outside. Someone would be like, what a wasted life, right? Because you didn't check them all. No amount of verification constitutes a proof, right? So I can plug in different angles from the unit circle or even with the calculator and show that the left side equals the right side. But that doesn't prove that it's always true. It just means that it's true in the cases that I tried. So in mathematics, how can we actually prove that it's true for all values if there's infinitely many values and we can't verify them all? Use variables. That's right. Did I mention that yesterday? Good. And it's still not raining outside, is it? Sprinkling, yeah. Stop me if you've heard this one before. Y'all didn't stop me. You like the story about the windows, right? Yeah. So there you go. We've reiterated the point. You use variables. That's how you do it. You use variables. So I'm going to prove this one to you, but it's a fundamental identity. So it's so basic that it's not the way that we're going to be proving bigger and better identities. Okay, but because it's fundamental, we're going to have to use the definition. So here's how we do proofs. We draw a line down the middle, sorry. And then we start on the side that has more information, because I didn't mention that to you as well yesterday also, that it's easier to tear down than build up. So the right side has more information, or it looks more complicated. So what we're going to do is we're going to replace cotangent of theta with its definition in terms of x, y, and r. What is cotangent in terms of x, y, and r? X over r. Now, in geometry, you would write the reason off to the side. Let's go ahead and write the reasons. Thank you. I heard R and I was like, okay, y'all drive the bus. Did you? Okay. It must be my hearing. That's right. This is the definition. I'm putting derivative. This is the definition of cotangent of theta. So I'm going to write the reason off to the side, because here's what you want to do. You want to realize that when you're doing a proof, the process itself is really the product. You don't want to skip a step. When in doubt, don't leave it out. If there would be a reason for having it, then you're going to want to make sure you do it. Okay, now I have a complex fraction. Hooray, hooray. So dividing by a fraction is the same as multiplying by its reciprocal. So that's going to be 1 times y over x. That would be, we'll just call that rule of division, right? State, change, flip. And notice I still have the 1 there. Now, what's 1 times y over x? Y over x. And the reason would be identity element of multiplication. ID element of multiplication. Good morning. And now what's the definition of y over x? Isn't that tangent? Yeah, that's tangent. And so now that would be definition of tangent. Now in geometry, maybe if you had a great teacher, you had to name the reason when you're doing geometry proofs, like parallel postulate, theorem 1.5 or whatever. And you could certainly do that here, but we're not going to do that. As long as you show every single step, we're going to assume that because you're showing enough steps, anybody who has modest understanding of trigonometry could follow from one line to the next. Now, how do you know when to stop? How do we know to stop there? Both sides equal each other's. Yeah, so when the bottom lines on both sides equal each other, you're done with the proof. In mathematics, we typically write QED at the end, which is a Latin abbreviation for quid erat demonstratum, which means we did it. Lo hicimos, we did it. Quid erat demonstratum, that which has been demonstrated. If you don't want to write that, sometimes mathematicians will put just like a little box down at the bottom to show that it's completed. That's kind of boring too. Sometimes I like to just sign my name. So I would encourage you to kind of put something that's unique to you at the bottom. You could put like bam or something, right? Like, or kapow, whatever. All right. So that would be the preferred way to do it, to start on one side and to stay on one side. The reason we draw the line down the middle is because when you're proving something, unlike what we did up here, where we multiplied both sides by cosecant, you can only do that after you're done proving it. When you're proving something, you have to work each side as a separate entity and manipulate it by either doing identities or keeping equivalent to the line above or below with algebraic manipulation until the two sides look the same. All right. Now, if you were stuck, you could jump to the other side. Like, let's say I got to y over x and I'm like, I don't know what to do. You could jump to the other side and say, what's the definition of tangent of theta? Well, it's y over x. And now, do both lines on both sides look the same? Yeah. So that would be fine. But that's not the best way to do it, but it's still correct. Because what you're doing is you're stringing together a sequence of logical steps that are equivalent. And you can hop in on any one of those lines and go clockwise or counterclockwise, and it's circularly all equivalent. Okay. So if you did jump to the other side, you're like, oh, that's y over x. Then you could just come back over here and finish it off like that. All right. But it doesn't really matter. I'd prefer you work on one side, but one of our strategies is if you're going to be stuck, jump to the other side and work a little bit, and you meet in the middle, right? So anyway, there it is. We used variables, and so now we know that's true for all values. So you could prove all the reciprocal identities in a very similar fashion. Okay. So that's the idea of proof. All right, so let's move along. The quotient or the ratio identities. I call these the ratio identities. Some people call them the quotient identities. Like the reciprocal identities, you also know these already. You do. Here's the first one. Tangent of theta is. If I ask you for tangent of theta from the unit circle, how would you find the tangent ratio from the unit circle? Y over x. Very good. And on the unit circle, the y represented which trig function? Sine. And x represented the cosine function. So y over x is really just sine over cosine, isn't it? Well, now we formally state it. Tangent is sine over cosine. Tangent sine over cosine. And what's cotangent then? Cosine over sine. Yeah, there it is. Those are your two ratio identities. Okay. So memorize those. But guess what? You already do. We call those ratio identities. So what's interesting to note now is you can write every single one of the 6 trig functions in terms of sine and cosine. That's kind of cool. Sine and cosine are obviously already in terms of sine and cosine, but secant is 1 over cosine. Tangent is, or cosecant is 1 over sine. Tangent is sine over cosine, and cotangent is cosine over sine. And that's why we're able to get the other 4 trig functions from the unit circle by just knowing x and y. Now, it's also interesting to note that these 2 sets of identities, they work for any power. Okay, so if you see something like this, sine to the 2nd power of theta, bless you, we read that as sine squared of theta. That's the condensed notation. This is condensed notation. It's kind of like having a zipped file. It looks prettier as a final product. It's easier to tote around with you, but it's the same as this. It's the same as sine of theta squared. This is the expanded version. And this one is good if we want to use it. All right. So if I actually wanted to evaluate sine squared of theta for a specific theta, I would write it on the right-hand side. I would find the sine of theta first, and I square the ratio. Okay. But we prefer to write it on the left just because it looks nicer and there's no parentheses, right? It has fewer things. The power is irrelevant for both the reciprocal and the ratio identities. So for instance, if you wanted to know what 1 over cosecant squared was, well, that's equal to sine squared, because 1 over cosecant squared is the same as 1 over cosecant times 1 over. I'll prove that. Let's actually prove that real quick. Okay, wait up for me. Let me look real quick. Okay, yeah, it looks right. So here we go. This would be 1 over cosecant. 1 over cosecant times 1 over cosecant. And then what's 1 over cosecant equal to? Sine. So by splitting up the squared into 2 things, I basically get 1 over cosecant, which is sine, times 1 over cosecant, which is sine. And what's sine times sine? Sine squared. Yeah. So I just proved that right there. So with the ratio identities or the reciprocal identities, as long as the powers match in the beginning and end, you're good. So for instance, tangent to the 5th of theta is sine to the 5th over cosine to the 5th. It's also equal to 1 over cotangent to the 5th. Lots of different ways you could do it, but the powers would have to match. Okay. Look what else we could do. Once we know these to be true, that tangent sine over cosine, look what we could do. I could replace sine with 1 over cosecant, and then I can replace cosine with 1 over secant. And then if I change flip, I get 1 over cosecant times secant over 1, and I end up with secant over cosecant. That's another identity. Tangent of theta is equal to secant over cosecant. Do you want to memorize that? Do you want to memorize that tangent of theta is secant over cosecant? You can. I'm not going to stop you, but I'm not, because I don't need to memorize it. As long as I know tangent sine over cosine, if I needed secant over cosecant, I could derive it using just the reciprocal identities, right? So the fundamental identities are just the most basic version that you want to have completely memorized so that you can build bigger and better things from it without having to memorize so much. Okay. All right, let's go ahead and prove this ratio identity. Cotangent of theta is cosine over sine. Don't forget your thetas when you write your trig functions. All right, so draw the line down the middle. That kind of keeps you from cross-contaminating things. Which side has more information, left or right? The right side. Now, because it's a fundamental identity, we got to go to the definitions. 1 over cosine is, cosine is x over r. Sine is y over r. So that's step 1. I'm not going to write the reason, but it would be definitions of cosine and sine. Whenever you create a complex fraction, as you'll see moving forward, you're going to get happy and celebrate, because the next thing that you're going to do is always going to be obvious. And that is going to be to eradicate the complex fraction. So stay, change, flip. That's your next step. Okay. Now, because the product is the process and the process is the product, it's kind of bad form to divide those r's out like that, because we want them to be visible. But they do divide out, and we're left with x over y. Okay. And what is x over y the definition of? Cotangent of theta. Yeah. So the left side looks like the right side, and then we'll sign off with something like, boy, howdy. Don't that good. There you go. So kind of get creative, make it fun. So now we know cotangent is equal to cosine of theta over sine of theta all the time, except when sine of theta is 0, right? It has to be of output on both sides. So if it's in the domain, it'll be the same value on both sides all the time, every time, never, not always. All right, so there's 2 sets of identities right there. You got to have them memorized, the reciprocal and the ratio. But didn't you already know them? Yeah, pretty much. Okay, so now we're going to move on to the new set. You haven't seen these before. These are called the Pythagorean identities, or I just call them the PIDs for short. The Pythagorean identities, PID. And they're built off the Pythagorean theorem. Okay, so here's the first one. Cosine squared plus sine squared is equal to, guess what? 1. Absolutely. What's another name for 1? 1. Cosine squared plus sine squared. Yeah. So that's an identity. It works. That's the version that you want to memorize. But once you have it memorized, you can manipulate it. Not while you're proving it, but once you have it memorized, you can manipulate it. So like if you wanted to subtract sine squared from both sides, you get cosine squared of x equals 1 minus sine squared. That's another identity, right? What's another name for cosine squared? 1 minus sine squared. What's another name for cosine squared other than 1 minus sine squared? 1 over secant squared. So, hey, I guess 1 over secant squared, since that's equal to cosine squared, must equal 1 minus sine squared, because that's also equal to cosine squared. You want to memorize that identity? No, we don't want to memorize that, because we can get that pretty easily from the other identities. But it's true. And similarly, sine squared is equal to 1 minus cosine squared. Okay? But you don't want to have to memorize that. So you can mess with these algebraically once you've memorized them and established them as being true. This one I call Papa Pid with 2 P's. Papa Pid. That's how he spells his name. Papa Pid. He's a single father. He's a dad raising 2 kids on his own. The other 2 Pythagorean identities are baby pids. Okay. So here's Papa Pid number 1, or Papa Pid. Cosine squared plus sine squared is 1. What's sine squared plus cosine squared? It's also 1, right? Flip them around, same thing. All right, now here's baby pid number 1. 1 plus tangent squared is equal to secant squared. of x, or theta. Now, here's the reason I call this guy baby PID. Here's why I call him baby PID. If you take Papa PID and you simply divide everything through by cosine squared, divide the left side by cosine squared and divide the right side by cosine squared, right? That preserves the equality. Whatever you do to one side, you got to do on the other. Look what happens. What's cosine squared over cosine squared? 1. What's sine squared over cosine squared by the ratio identity? Tangent squared. Yep. And what's 1 over cosine squared by the reciprocal identity? Secant squared. There you go. That's baby PID number 1. Call it asexual reproduction. Okay. No mama PID needed. Just Papa PID shoots out an offspring. Divide through by cosine squared. You get baby PID number 1. All right. So what's another name for secant squared from the Pythagorean identities? 1 plus tangent squared. And what's 1 plus tangent squared equal to? Secant squared. Good. So that's the way you want to memorize it. All right. Now, of course, once you have it memorized, if you wanted to subtract tangent squared, you can also get secant squared of x minus tangent squared of x, and that would equal 1, right? Manipulate it. Secant squared minus tangent squared is equal to 1. But 1 is also equal to cosine squared plus sine squared. So I guess cosine squared plus sine squared must equal secant squared minus tangent squared. You want to memorize that? Nope. Nope. Just memorize that 1 plus tangent squared is secant squared. And then you can manipulate it if you need to. Now, baby PID number 2 comes from the exact same Papa, but now instead of dividing everything through by cosine squared, if you divide everything through by sine squared, instead, what do you get? What's cosine squared over sine squared? Cotangent squared, yep. And what's sine squared divided by sine squared? 1, and then 1 over sine squared is cosecant squared. So that's baby PID number 2. And then you flip the first 2 terms around. So notice if you have baby PID number 2 memorized, or baby PID number 1 memorized, baby PID number 2 is easy to memorize, because really, instead of dividing it through by sine, what do you notice about the names of the functions involved? On the left, in baby PID 1, it's 1 plus tangent squared is secant squared. And in baby PID number 2, it's 1 plus cotangent squared plus cosecant squared. All we did to get to baby PID number 2 is put the co-functions in where the functions were. Just add cos to both of them. Okay. Oh, yes. Looking good, babies. All right. So add cos. So memorize those, memorize those, memorize those. I put in the Canvas announcements yesterday some links to flashcards for Quizlet. So some people like to do that. So there's a bunch of them already there. But you do want to memorize them, okay? Because if you don't have them memorized, it's kind of like bushwhacking with your mathematical machete, but you don't not only have a map, but you are like, you have no idea where north and south are. You're just kind of like aimlessly wandering around a jungle going in circles. You don't even know what your options are, right? All right. So let's go ahead and do example 3. We're going to prove Papa PID. We're going to prove that cosine squared of x plus sine squared of x equals 1 for any angle x. It always is. Okay. First thing we do to prove it is draw a line down the middle. And then we choose the side to start on. Which side has more information, left or right? The left. Now, because I'm going to use it, I'm going to start by writing the condensed version in the expanded version. So this would be cosine of x squared plus sine of x squared. Kind of like when you send a compressed file to a friend or whatever through an email. I don't know if that you do that as much anymore, but you used to have to zip files and then you have to unpack it on the other end to use it. This is the unpacked version. Now we're going to, because it's a fundamental identity again, we're going to replace this with their definitions in terms of x, y, and r. So it's still cosine squared plus sine squared, but let's write their definitions. What is cosine in terms of x, y, and r? X over r. And what's sine? Y over r. So you don't have to write the reasons off to the side so long as you're showing the step. All right, now we're going to use the rule of exponents from the earlier in the year. X over r quantity squared is the same as x squared r squared. And y over r quantity squared is y squared over r squared. Now here's time for another strategy. When you're starting on the left side, the right side becomes your target. I'm starting on the left, and every time I'm doing another line, I'm looking at the right side because I want to make sure I'm getting closer and closer to my target. You don't want to be moving away from it for too long. Sometimes you might kind of take a scenic route, but I noticed that the right side is a single term. It's one term. My left side has two terms. Yes, two terms. And now they're fractions. In order to combine two fractions into one term, I need a what? That's when you're multiplying. Common denominator. All right, so that's the strategy. Look to get a common denominator when you have fractions if you're trying to get to a single term when you have more than one term. Well, do I already have a common denominator? Yeah, so that was convenient. So now I can say it's all over r squared, and the top is x squared plus y squared. And now what do I do? If you're doing a proof like this and you're not sure what to do next, can you just say, well, I know it's supposed to equal 1, so I'll put a 1 there, and then I'll sign off like ole. Will that work? You think you're going to fool me?
No, you can't just pull a matador.
No, you can't just pull a matador.
You can't just get the answer and then pull it away at the last second.
Right. No, don't do that. Don't do that. You got to show me your step. Now, it is equal to 1, but guess what we have to show in between those two steps? One more step. Can I just take the square root? If I take the square root of one side, I have to do it to the other, but I'm not allowed to do that to both sides here because I'm in the process of proving it, so I can't cross-contaminate. I can go to the other side where there's a 1, and I can try to start building it up to make it look like x squared plus y squared over r squared, but that would be like building a homestead, tearing it down. No, I can't take the square root. No, that doesn't work. That would be like taking the square root again. Can't do that. Hey, what about
Can't you times it by r?
not by r, but I can multiply by r over r.
I was saying like times both sides by r.
Oh, ooh, you just said both sides. What did I say? Why did we draw that line down the middle? We are not allowed to cross-contaminate when we are proving. After we prove it's true, then feel free to manipulate it however you want. Okay? But we have to work at it as an individual expression, so it needs to remain equivalent the entire time. What can we do? We can multiply by clever forms of 1, because anything times 1 is itself. We can add clever forms of 0, because anything plus 0 is itself. We could divide out common factors, get like terms together. Yeah, I mean, that's legal. Will that help me though? Does that get me closer to 1? No. Okay, so at this point, we have to think about angles again. When we had reference triangles, here's theta. Remember, this point was the point XY. So this was X and this is Y. And what did we call the hypotenuse? R. Is there any way to relate X and Y and R to each other in a right triangle? Pythagorean theorem. X squared plus Y squared equals R squared. Well, I'll be a monkey's uncle. That's like the A squared plus B squared equals C squared, but it's in terms of R variables. So guess what the numerator really is equal to? The numerator.
So it's all just r.
Right. I'm going to do an identity substitution. This is an identity right here. I'm going to replace x squared plus y squared with what it's equal to. It's equal to r squared. And now what's r squared divided by r squared? 1. And now do both sides look the same? Yes. So now Olay.
After some like spaghetti rolling.
Yes. Finagling, skedaddling, whatever. Yeah. So what we're doing is essentially doing some substitutions with identities and then a little bit of algebra. Substitutions, algebra, until we get where we want. And if we go down a path that's not bearing fruit, we'll just back up and retreat to a line where we want to start going in a different direction and see if we get it. So it does take a little bit of persistence. The worst thing you could do is just to stare at it and say, I don't know what to do. Do something. Do something. If you don't know what to do, you haven't been paying attention algebra. Each of the 6 trig functions. Next set of odd functions. How would you find the complement? cosine of is the x, horizon